Thank you, Sai Kiran, and thank you for the opportunity to speak about the research that we do here at Rice University. It would be wonderful to have come down to University of Waterloo, but this is great. Thank you so much. As Sai Kiran mentioned, today I'll be telling you about this really very interesting new class of semiconductors, which are called halide perovskites, and uh, and their journey, especially in the field of photovoltaic devices. And specifically, I'll be talking about a subclass of these perovskites, which are called these two-dimensional halide perovskites, which is what we've been working on since over about 5 to 7 years now. And the main mission of using these materials is to overcome one of the key bottlenecks that has prevented its commercialization, and that's achieving long duration stability. And so that's kind of been our effort over several years, and we've made tremendous progress in that arena, which I hope to share with you. Okay. In addition to this, the other role I serve, being apart from being a professor, is I also direct Green which is Rice Engineering, is Rice University's School of Engineering's energy transition initiative. And so below this, we have a lot of different areas that we work on, and I'll give you a little bit of flavor of things as well. So, just to begin, just some things about what's going on in the group. So obviously there is a big focus on looking at perovskite chemistries and light matter interactions and lattice dynamics. Looking at questions such as what happens when you take these are solution process semiconductors, and so what happens when you take these inks and put them in solutions, what happens to how do you make these films, understanding crystallization kinetics, and how does this really impact the performance and stability. And so I'll talk a lot about that. As Sai Kiran also mentioned, we just launched a new company. It's called Direct H2, and here's a picture of this. The idea is it's a photoelectrochemical device, which we think we have a major breakthrough in. We can get very high solar to hydrogen conversion efficiencies, almost approaching 25%, and also get really long-term stability, which has been a challenge in this field. And so we think that this all this requires is sunlight to function. So there is no electricity needed to power this type of a device, unlike electrolyzers for hydrogen and for CO2 and whatnot. And so this we think is the greenest way of doing this, and we can do it using really low cost materials. You don't have the cost of electricity, which puts us really on track to get to $1 a kilogram. There's also a lot of work on quantum emitters. It's really derived from this work on understanding crystallization, and so we're working on that, and I won't talk so much about that. And then finally, we also have a big program. It's a $12.5 million program that we've started on plasma chemistry. And the goal here is to convert CO2 into valuable products. And we made tremendous progress on that. And I won't talk about this. In fact, there may be a startup company that may come out very soon from this. We feel we have a major breakthrough with CO2 conversion, both fundamental but even at scale. Okay. So today I'll really be talking about these things, which is just take you tell you a lot about halide perovskites, but I'm happy to discuss other things if there's interest, and tell you more about that as well. Okay. Okay. So CO2 global emissions. This obviously is a major that's the backdrop of what we are kind of trying to do. Let me just move this guy here below so it doesn't bother me here. Okay. And these numbers are very big. 65 gigatons a year is our CO2 emissions overall. And the goal, which was set, of course, is by 2030 to see if you can actually halve this, right? And by 2050, get rid of this completely, right? And that would then put us in track for getting to this 1.5 degrees C rise in your sea levels and whatnot. I'm sure you've heard this narrative before. And if you think about what are the key, which are the key um, sectors which are responsible for this, there's manufacturing, of course, which are industries, hard to abate industries like chemical manufacturing, oil and gas. But then if you just forget about that, two sectors which play, which could really play a big role is electricity generation, which is typically done through coal power plants today. And the second is transportation, electrifying, EVs and things like this. And so if you just take these two in mind, and if you just solve that problem, then that constitutes about 50% of CO2 emissions that we have. And so that's kind of very interesting because which means that if I have renewables and things which are powering this, then we should be able to really make a big dent into this. Okay. And whenever you talk about energies, I think one of the main things that drives this is scale. You're talking about technologies that can scale, and that's really what drives things. So oftentimes what you have to do is think of, whatever you're doing in your lab, you think about technologies which are scalable. And if they're not scalable, then they're not going to really make it, and they're not going to really have an impact in this the scheme of energy transition. Okay. And I encourage you to, if you've not seen this book, there's a very famous book by John Doerr, which is called Speed and Scale. And he gives you really a roadmap of how you would go about, doing this. Okay. So I encourage you to read it if you've not seen this, or this website, at least check this website out. So, all right. So we're talking about scaling, and we know how to scale. In fact, semiconductor industry knows this very well, and it's demonstrated scaling. So I don't know if you're familiar with this, but there is something which is called the Moore's law, and this was implemented for transistor scaling. So what I'm showing you is the number of transistors on a chip and the years, and what he said was an empirical law which said that the number of transistors doubles every year, and that kind of continued along, whereas now we've now beginning to hit some fundamental bottlenecks. And so that's kind of the whole idea, that you want a technology that can really scale, and one such technology is photovoltaic devices. In fact, photovoltaic devices have demonstrated this type of logarithmic, or exponential scaling, and this is where we are going with it. This is from the International Energy Agency roadmap, and we are well on our way to getting to, very high capacities, almost approaching terawatts by 2030. And so, in order to do that, we need really fast installation. 3x times fast installation is required to get to those type of numbers. But nevertheless, photovoltaic devices do demonstrate this exponential scaling which is required in most clean energy technologies these days. Okay. And solar is great because really you're getting the energy from sunlight, but one of the major issues with solar is that its intermittency. Obviously, the sun doesn't shine, every day, all the time, not 24 hours. And so you get maximum sunlight typically, if you have a solar farm, this is what it'll look like. That typically it'll peak at noon. And then, of course, in the evening and in the morning, the sunlight's really, the solar flux is very, very weak. But that's where you really, make electricity in the middle of this. And so, on average, if you think about the capacity factor, which is the average power generated in 24 hours divided by the peak power generated in noon, what you find that these capacity factors are very, very small, about zero point 0.1 or 0.25, which is right. And so these are very, very small. And so the only way this can be sustainable in general is that you want to make the cost of PVs very, very cheap. In fact, there is even a proposal where, what if your panel was completely free of cost? And then what you would do is you would use some amount of money that's left. If you sell your panel for free, then you have the leverage to add a storage element to your, solar farm. This may be, a bank of batteries, or it can be some electrochemical device, or anything which makes fuels, anything. But I think that's the idea, that you make solar or renewables energy so cheap that you can now also add storage, which otherwise you have to pay for. And typically, every storage technology these days is quite expensive. Okay. And so the goal is that how do we get to something like 5 or 10 cents a watt, right? And that's really, really cheap. Silicon today is anywhere between 20 to 60 cents a watt, right? Even though there's been tremendous advances in manufacturing in China, but that's where we are. And so if you get to these type of numbers, then that will put us well below 2 cents a kilowatt hour, right? Which is the levelized cost of electricity. And in fact, in some places in the world, like Dubai or, in the Arab countries, this cost is already at 2 cents a kilowatt hour, right? And and so that's the whole idea. And what DOE is put out as this plot, which is, which plots the levelized cost of electricity as a function of years. And Solar Energy Technologies Office, right, has set a target of getting to something like 5 cents a kilowatt hour, or even below that. In order to do that, you need new materials, because if you look at the equation for the levelized cost of electricity, you see that the efficiency always sits in the denominator. And so if you can increase the efficiency of your system, then you're going to lower your cost much more drastically. Because yeah, sure, you can do things like reduce the module cost and all that, but you'll really, hit a certain, saturation, because you can't really change that beyond a point. Okay. And so, how do you increase the efficiency? Well, you look for new materials and new physics, but you can also think of multi-junction solar cells, right? And where your efficiencies go beyond what a single junction can do, beyond 25%, over 30%. And in fact, that's sort of been the scheme of what people have been trying to do. So that's kind of the goal. If you keep making your efficiency higher and higher, then your levelized cost of electricity goes down. You need less land mass to also put down your panels. And so you really, everything scales kind of linearly in terms of efficiency and the land mass that you need. Okay. All right. And so how do you do that? In fact, what I'm showing you is this plot, or a derivative of a plot that NREL puts out. It's the solar cell efficiency as a function of years. And you can see that this yellow line here is that what has happened to the halide perovskites. And you can see in just about 10 years, the efficiencies have surpassed that of silicon, right? And so that's been amazing in terms of just a materials platform. For example, for silicon to get to 26%, it has taken something like 40 to 50 years. Right. And that's happened for perovskites in about 10 years. So that's been remarkable, and that's attracted a lot of attention. In fact, what people have also done is taken perovskites and combined that with silicon. And if you do that, you can see these efficiencies go even higher. And this goes to about 33.7%. This, I think, is the peak, or maybe even 34, which is a silicon and perovskite tandem, which means that you don't have to change the manufacturing of silicon so much. Just put a layer of perovskites on there, and you now start to get efficiencies that are quite high, and this is where you start to get real lowering of your levelized cost of electricity. However, this has not been such a big problem. The big problem has been achieving long-term stability of halide perovskites. And I'll tell you more about why this is an issue. But before that, I want to show you this thing, which is this levelized cost of electricity as a function of lifetime of your panel, right? So if you make a panel, and it turns out that your levelized cost of electricity is a function of that. Obviously, if you have a panel which goes more than 20 years, then your levelized cost of electricity is lower, as opposed to a panel that lives for 5 or 10 years. And so if you think about perovskites, we don't know where we are. And so I kind of arbitrarily put down a star here, right, in terms of where the stability is. And maybe this is 10 years or 15 years, but we are definitely not there yet in terms of 20 years. However, some of the breakthroughs that I'm going to talk about today, we feel that we've achieved this type of the stability that is required to take this technology and really, put this into the market. And we are working with major companies who are trying to license the IPs that we've written on this, on the perovskites. Okay. All right. So that's the whole idea here. Now, when you talk about halide perovskites, you're really talking about its use in photovoltaics. And here I want to just talk about a few things. Oftentimes people do a lot of work on materials, and one of the ways to think about materials is to think of, if you're thinking about what you use that material for, apart from its fundamental, properties, and is that what is it that you would use that material for, which no other material can do? right? And you'll find a lot of materials which you can use for a lot of things, but very few materials which are specifically, specifically you can overcome the state of the art of a specific technology. And so halide perovskites are one of these things which give you efficiencies which are beyond that of the state of the art, which is silicon, right? So it's really made for making really efficient solar cells. Now, since we are going to be talking about solar cells a lot, I want to spend a slide on just understanding what how a solar cell works, right? And so I'm guessing that a lot of people may not be from this background, but I see that there's a big program in electrochemistry. It's not very different in that sense. So let's think about that. So, I have a stack of a material, right? And there's a material, there's certain layers which are for passing your or filtering your charge. But there's a material which will absorb the sunlight. And in this case is a halide perovskite for us. So a solar cell is really any material, and typically it's a semiconductor that absorbs light very efficiently, and then we use charge selective contacts, which means I can filter out the electron or the hole, which is the positive particle, selectively, and I can move them across in different directions. And if I can do that successfully, then I've made a really good solar cell. I don't need a PN junction for doing that. Typically, in a silicon, this is done through a PN junction, but that's not required. It can be any semiconductor which is intrinsic, which does not have, and it's not doped, but can do this job of selective contacts, which can be pulled out. Okay. And so I'm showing you a typical solar cell curve, which is in the middle here. And you can see this is the dark curve. So it's a diode, which means it passes current only on one direction. And now when I put light on this device, what I start to get is a photocurrent, which gives you the short circuit current. And so everything moves down in the negative direction here. And so you're now generating a current, but you're also generating a voltage, right, in this device, right? And so you see a curve like this, and so that's where you get this photovoltaic effect. And so there are three things. One is the short circuit current, which is shown as this JSC here. So let's think about what that is. So that is basically what you need is a material that will absorb light, right? And it'll generate electron hole pairs. And you want to be able to collect these devices, these electron hole pairs before they recombine. And so that's how a current is generated. For example, I create electrons in holes here. And so if I can extract my electron and hole before they recombine in the semiconductor, then I've generated current in the device. Now, if you think about the other two factors, one is something which is called the open circuit voltage, right? This is analogous to an OCV in an electrochemical cell. And the idea here is that if I take this and if I look at this point here, I am not passing any, this at this point, I have a semiconductor. My device is an open circuit, which means that there is no current that is flowing in this device, right? And so this gives me the point where I have only generated voltage. And so this is all thermodynamically determined. The maximum voltage I can get is equal to the band gap of the material, right? This is really the potential energy that I can get because that's determined by the band gap of the material. And it's actually thermodynamically determined. And obviously, in order to get power out of this device, like in a fuel cell, I need to multiply my voltage and my current. And so I need to do that. And so if I multiply the two, I get something which I generate a power. And typically, in order to do that, I need to give away some amount of voltage, right? So if I am here, I need to lose some voltage in order to come to this point. So I need to compromise, right? And similarly, if I am at here, it's a short circuit current but no voltage. I need to lose some current in order to gain some voltage. And so that compromise comes from statistical mechanics. It's thermodynamics, really, and statistical mechanics that you need to be you can't have best of both worlds. You need to give, and so that compromise gives you then it brings you to this maximum power point, and that's where you drive your device. Now, what is that? And that's really determined. That's really called the fill factor. And you can in therm it's also coming it also comes from thermodynamics because you're now losing some voltage to do this, and it is really the ratio of this what your actual max power is as to what maximum you can get, which is basically determined by your maximum short circuit current and VOC. And so the best you can do is like 89%. So if someone comes right with a device and shows you a fill factor which is more than 89%, then you are really violating thermodynamics. That doesn't, it's not possible to get something more than that. Okay. And so what you're trying to do is maximize your voltage and your current and try to maximize your uh, maximum power point here. Okay. Very good. If there's questions, please stop me and I'm happy to answer them here now or even later. Okay. Okay, so bringing me to the topics for today, I'm going to talk about then in the context of, how do we really get efficiency and stability of a solar cell? And so I'll talk about the specific work which came out in 2022, which is creating these stacks of 3D and 2D perovskites. And then more recent work, which is, in these two papers. In fact, this paper is still in revision, but this came out in 2024, is how do you again combine 2D perovskites with your 3D perovskites in a meaningful way. And the goal that we had set ourselves was to be able to achieve, do a stability test which has never been done before, which is at 85 degrees C under one sun illumination, right, at maximum power point. And so 85 degrees C is an accelerated test, which means all the processes or all the degradation processes that occur are accelerated because now the kinetics of your process are faster. And so if you can survive this test, if you can get a device to do this, then that really can be extrapolated to really long lifetimes. And so when we did this, there was no real work, and there was no solar cell which could survive this type of a test. Okay. So that's what we will be talking about. So let's start by talking about 3D perovskites, and I'll just take a second here. And if there's questions, I'm happy to, answer them. Okay. So let's talk about 3D perovskites and the tolerance factor. So 3D perovskite is basically, perovskite is a type of a mineral, and it forms this AMX3 or a ABX3 structure, where A is your cation, right, and this is typically a monovalent cation, things like formamidinium, methylammonium, or cesium. It's got a +1 charge. Then I have a metal which is in the center, right, which is the M, and that's typically things like lead or germanium or tin, and that has a divalent charge. It's a 2 plus side. And then I have the halides, which are at these apical sites. These are the X, which is in the iodine, bromine, and chlorine, and that's an anion, right? And so when I take these things and I mix them together, I can form a halide perovskite. And now, if I take the ratio of these ionic radii, it gives me a certain value, right? And that value is known as the tolerance factor, and it's called the tolerance factor because it tells me whether I have made a perovskite successfully. So it turns out that if I took this and if I put these three cations and if I made the perovskite, there are three types of different perovskites I could make. One is I can make a formamidinium, right? Which means Fa is my cage cation here. It's the monovalent cation. And I form essentially this type of a structure. And it has a tolerance factor of 1, right? Which is right on the edge. Then if I, instead of Fa, if I take Ma, then I have a tolerance factor of zero point 0.9, right? And then if I take cesium, then I have a tolerance factor of zero point 0.8. Now, a perovskite is anything that falls between these ranges here. So you can see that this is right on the edge. It's a little bit too big. This is a little bit too small, but this material is absolutely perfect. And so methylammonium lead triiodide really works the best, and you can make a very nice perovskite with it. Whereas in the case of FAPI and in terms of cesium lead iodide, you find that you can't make a really good perovskite. In fact, at room temperature, it exists in something which is known as the delta phase or the yellow phase. You can see there are these separated islands of these perovskite-like structures, and that's known as a delta phase. It's a polymorph of your formamidinium lead triiodide. Similarly, the cesium lead iodide also does the same thing because it is too small, right? And so it cannot accommodate this, the stresses that are involved. It's electrostatic interactions which are very strong, and so it doesn't balance the charges and gives you something also which is the yellow phase. So the only thing that forms is this methyl ammonium tetraiodide, but because methyl ammonium is very hygroscopic, it tends to degrade very quickly. In fact, if I take a film of this and put it outside, it's going to basically, water is going to attack it and it's going to hydrolyze, and it's basically going to give you, it'll go back to its fundamental elements. So this is a big problem because the material that forms it is this one, right? But it's not stable at all. And these two, which you would like to use, are not. They don't really form a perovskite. And so what people have done, and I'll talk about that. So okay, so these are the 3D perovskites. Now let's talk a little bit about the 2D perovskites. The 2D perovskites are the same, almost same as the 3D, but now in addition to what I put in the 3D, I also add one more thing, and I add a bulky organic cation. Things like a butyl ammonium, or something like a 4-AMP, a piperidinium molecule. And so what that molecule does is it cannot really go into the structure, but it forms, it likes to settle. It forms this. That's why it forms a layered structure, assembles into a layered structure into this form, and it has this formula. So you see that this part remains the same, but now I have this A2 prime, which is this bulky, in this case was a butyl ammonium, basically a 4 carbon chain. And that forms this structure, which is a layered structure, and it settles, it spaces, it sits as a spacer cation between these octahedral layers of the perovskites. Okay. And you can have small configurations or changes in it, and it can form something which is known as a Ruddleson-Popper phase, or a Dion-Jacobson phase, or an alternating cation phase. These are just small structural changes, or changes, differences in the structural elements, just the way the unit cell is offset from each other. But the nice thing about this is that you can now chemically tune these layers, right? So what I call the N number, which is the number of layers that I have, just like you would tune your size in a quantum well, or in a quantum dot, I can keep changing. I can control this chemistry very well, and I can change the number of layers. So you can see I can go from N1, 2, 3, all the way to 6. And of course, these are spaced by these organic cations. And obviously, when I do that, what I'm changing is the confinement, right? Quantum confinement in this material. This is a typical particle in a box type picture, N1 to N6. And you see very nice, red shifting. This is coming from decreasing quantum confinement. And you can see the 3D absorption is here. This is the bulk perovskite that you would have. This is the corresponding photoluminescence. Again, you can tune this color very nicely. Okay. If you think about now, obviously you want to be able to, move charge around with this material. And so if you think about the band structure, right, the electronic structure, people calculated this, and you can see that this is what it looks like. This is energy versus the symmetry points in, this Brillouin zone, essentially, if you will. And you can see that this is this is a direct band gap material. It's centered at this gamma point, which is this one here. And you have, it's at the same K value, which means the direct band gap material. And you can see these curves, they're very nice, and which means that charge can really move across these valleys very nicely, right? And which means that electrons, when you put this here and move it, it has a nice slope where which it can move, and which means these materials have very nice, dispersion, or curvature, where you can get nice mobilities in transport. Okay. So this is what the 3D perovskite is, and that's the same essentially for a 2D perovskite, except that if I, so this is for the 2D perovskites coming from the same octahedra, which is essentially the metal iodide, bond that I have. But now if I go in this direction, right, if I do the same dispersion, which is this gamma to X, right, in this direction, then you see that I have an organic molecule here, and this organic molecule is insulating, which means that instead of getting these nice curvatures, I have these flat bands here, which means that if I place a charge here and try to apply an electric field, this is not going to go anywhere. In fact, I'm going to have, going to have terrible charge transport in this direction. And that's indeed the case, that if I try to move your carriers in this direction, then you have really bad charge transport. Okay. So those are the differences. It's essentially the same, except that now in a two-dimensional perovskite, my third dimension, right? I have an insulating organic layer, and which means that transport can only occur in two dimensions. Okay. And so, we started working on this material really, earlier on. And this was really a seminal paper. It's back from 16 during my days in Los Alamos. And we showed that, in fact, by tuning the 2D perovskite somewhat, you can make an efficient solar cell, right? You can make something which is about 17% or something like this, or in that time it was 12. But most importantly, what you can get is really good stability compared to the 3D perovskite. The presence of these organic layers, like these bulky organic cations, makes it hydrophobic, and it also prevents your ions from moving about in your material. And so we showed that your 2D perovskites have very good stability, both under light illumination and also under 65% humidity compared to your 3D perovskite. And so that was really, something that triggered this field. And people have been trying to use the 2D perovskite, somehow combine this in a way so that you can use the efficiency of the 3D perovskite, which is over 26%, but use the stability of the 2D perovskite, right? So combining the efficiency of 3D with the stability of the 2D perovskite. And in fact, that's been really the approach that people have been doing. Can we combine? That's the question we asked as well. Can we combine these two things so that we get something that can imbibe the properties which are, the best properties from each of these materials? Yeah. And so there has been multiple schemes of doing this, right? So people have basically done different approaches to this. These are the common ones, where they take these, they take these 2D salts and they mix them in a 3D film, and you form these, islands of 2D perovskite with different band gaps, and they call this quasi 2D. Or sometimes they'll take cations that make the 2D perovskite and dope them into or you mix them, you use them as an additive in a 3D, and you get something which looks like this, where your 2D perovskites are at the grain boundaries of your bulk perovskites. And the third most popular approach has been taking, one of these cations that you have, right? And you disperse them in a solvent which does not dissolve your 3D layer, right? So if I take this and I spin coat it on top, the cation, then what the cation does, for example, if I take butyl ammonium in isopropyl alcohol, which does not dissolve your 3D perovskite, then this cation can steal some of this lead iodide or from your 3D and form a very thin layer of your 2D perovskite on top. Essentially, this is like a passivation layer that you get on the top of your 3D perovskite. Okay. And so, we've been kind of thinking about how to go about this, right? And one of the approaches that we took was quite different, right? So, what I'm showing you is basically these precursor materials that people use for making the 2D perovskites. And what they normally do is they take these precursors, they mix them in solvents, and then they cast films of this, right? And we call this the classical method. This is what has been used in the literature. But instead of doing this, what we did was we take these materials and first make these single crystals, the ones I showed you, which had these very nice resonances. So we can control that n number very well. And we made these type of crystals, right? And we take those crystals and then dissolve them into the solvent that we want. Okay. So compared to what has been done, we take these pre-made crystals, just one extra step, right? You can make these in large quantities, you dissolve them in there, and then we cast a film. And we call this method the phase selective method. And so it turned out that when we did this, we started getting films that had very high phase purity. What do I mean by that? Which means that when I make a 2D perovskite, for example, if I look at the plot here, then what I get is in the absorption spectra. If I'm trying to take a crystal which is n is equal to 3, which is only 3 octahedral layers, then I'll get absorption coming from exactly that N3 perovskite, right? 2D perovskite, not from other phases. Okay. So if I take this and if I do this, we were able to control and see that When I take these N3 crystals, dissolve it, I get really a film that is phase selective, which means it's very selective to the N3. Similarly, if I do this using the classical method, which I showed you, right, which is this, then we were getting films that had mixtures. For example, look at this peak here, look at this impurity here, and then you can see this tail, right? And it extends all the way to that of a bulk or a 3D perovskite. And so we were getting these mixtures which were not very pure. Okay. So we found a way to get a 2D perovskite film that's very, very pure in this case, more than 90% pure. And we do have small impurities, which is shown by this little star. And you can get the same in X-ray diffraction. Typically, you get these peaks which are equally spaced. This is, look at the red curve here, and that is a signature of a phase pure 2D perovskite. Now, this really led us to an hypothesis that what was really going on, right? So, what made us get these pure phases? And so, one of my students was working there who was a big fan of Harry Potter, and so this is kind of like similar to if you think about, Dumbledore, where he pulls out his memory, right? And he puts this in this sort of this memory vial, right, in this solution, and then he puts this into the pensieve, and then he can see you can actually make this is like filmmaking, right? And so we were doing something which was quite similar like that. You were taking these 2D perovskites, right? These are crystals. There's N1, 2, 3, and 4, right? You were dissolving that into the solvents, right? And then you were making films of this material. Okay. So this was kind of what came to us, and this led us to a hypothesis of, what's really happening, right? What's happening in the solvent that allows us to get these films, and then what are the kinetics of this filmmaking process, right? How are they different compared to what people have been doing? Okay. So we set out to understand that. And the first experiment that we did was something which is called dynamic light scattering. Basically, what you're looking at is a light beam that is going through your solvents, which are like this. And one of them is this classical one, which has, all these precursors mixed. And then the second one is where we take these crystals and we dissolve them into the solvent. They both look identical, but when we look at the dynamic like scattering, they give you very different results. So the classical sample, you see that you get, a curve, which is, one single exponential. And when you actually extrapolate what that size is, right, of the particles within this, it gives you something which is of the order of a nanometer of less than nanometer. And so this is consistent with the size of lead iodide particles that you have, right? They have a radius of about zero point 0.7 nanometers. And so that was consistent with it. Whereas in the phase selective method, where we added these crystals, now what you start to get is two distributions, right? So you have the first distribution and the second one. The first one matches that of this lead iodide. Obviously, there's lead iodide in the system, but the second one gives you a much larger distribution. And that distribution is of the order of 200 to 400 nanometers. So you have these crystallites which are in the solution. These are colloidal things which are in this solution, which are stable. Okay. And so this now is giving you basically something which is very different, which means that these crystals that we added into the solution somehow have found a way to remain stable in the solution. They don't completely dissolve. Okay. And in fact, you can go and measure the absorption of these seeds which are in the crystal. And so we did this. This is for N1 solution, N2, N3, N4. And you can see now you start to get this absorption, right, which corresponds to the crystallites the crystals that you added, right, to these different peaks that we were getting. If I showed you, and that's what it matches, which told us that not only are these crystallites present, but they retain the electronic properties, right, that you have, the optical properties and the electronic properties of the crystals that you have added. And so that's where we coined the term that somehow they retain the memory of what the parent crystal is. And so we call them these memory seeds. Okay. And in fact, they have also very different nucleation behavior. You can actually see that in the phase selective method you get this very nice nucleation of the film. It's from a point source. These are all these seeds which are nucleating. Whereas if I compare this with something, with the classical method, you see this very weird type of dendritic, growth of the films, which gives you a lot of defects, right? And so these memory seeds then dictate the nucleation that you have. And in fact, you can make these films and show that these films are very, selective. This is kinetics of the film formation. And you can see this N3 film, and dominantly an N3 film with a small impurity, whereas in the classical method, you have N2 and N3, and then also this tail, which is, which is all these impurities. Okay. So now you can take a crystal, you can make, put this in a solution and make a film that's very, very pure N2 of 2D perovskite. Okay. And so we made these films and we got very nice efficiencies, about 17%. They were not 25 or 26% like the 3D, but nevertheless, these were very nice numbers and very nice efficiencies. And they demonstrated stability like, we had measured earlier back in 2016. Now, the next question was, how do we really combine these 3D and 2D? And so one of the issues that we always run into when you do solution processing, and maybe some of you have done this, is that if I have a film of 3D perovskite, and if I want to put down another layer on top, and if that's also a perovskite, then I have to worry about the solvents that I use, because I don't have solvent compatibility, right? Because this is after all also a perovskite, which means whatever dissolves a 3D also dissolves a 2D. And so when I mix these 2D and I put this on, right, using this memory seed method, the chances are that I will dissolve away this 3D perovskite which is underlying. Okay. And so we were thinking of how to do this. Of course, what we wanted to do was come up with a method without washing away, where we can create these type of stacks. All right. And so we looked at, so this is a complicated plot, but we look at a lot of the design criteria for, what are the different solvents involved. Okay. And so here's what I'm showing you is the donor Guttman number of your. Basically, this is the ability of a solvent to solvate a Lewis acid, right? And you may have learned this in chemistry, right? So this is the donor Guttman number, and this is the dielectric constant or the dielectric permittivity of the solvents. And you can see there are all these different solvents that we've listed: non-polar solvents, polar protic solvents, polar aprotic solvents. And so it turns out that there are these sets of solvents which are below a certain dielectric constant, which do not dissolve any of the perovskites, right? Acetone, IPA, they don't dissolve it, right? But if you look at these solvents, these are these polar aprotic solvents, things like DMF and DMSO and DMPU, all these derivatives. It turns out that these green dots here, which are above the dielectric constant of 30 and above a donor Guttman number of 18, can dissolve both the 3D and the 2D perovskite, which means I can take these precursors, put them in, and they really dissolve away your 3D and 2D both. Now, it also turns out that there are some of these solvents, right? Things like acetonitrile, TMS, polypropylene carbonate, ethylene carbonate, which are, I think, ionic liquids. They We found that they actually dissolve the 2D but not the 3D here, right? Which was very interesting and quite unique, because what this meant is that I can now take a 2D perovskite, dissolve them in these solvents, and then do my solution processing to put this on top of a 3D perovskite. Okay. And so this was quite interesting for us. And then, of course, there was some solvents, in this case, for example, NME, which does not dissolve both the 2D and the 3D. Everything just crashes out. Okay. And so we set out to do this, where we took acetonitrile, and using our memory seed method, we put everything inside, and we dissolved the 2D perovskite in this, right? And these are the two structures, 3D and 2D typically. And so we wanted to do that. And so we wanted to understand what makes it really dissolve a 2D but not a 3D perovskite. Okay. And so if you look at these basic interactions, right? So what I'm showing you is the strength of these Lewis acid-base interactions, which you may have done. This determines solubility. For example, what I have is a solvent, which is a Lewis base, and then I have lead iodide, which is a Lewis acid. Okay. And typically, when you mix this, they form an adduct first, right? And then you form a perovskite. And now, depending on what solvent you choose, that depends on the structure of the perovskite. Now look at these 3D perovskites. They are basically a three-dimensional network, and they have a strong ionic bond, right? They are essentially, complete network of three in ionic bonding here. And so you need a solvent which has a high Guttman number, right? A donor number which is greater than 18 in order to break this bond, right? And that's what we saw. In fact, you need a donor number which is greater than 18 here in order to dissolve a 3D perovskite. Okay. But if in comparison, you see the 2D perovskite, which is a layered structure. So I don't have this 3D network. In fact, I have a 2D network, and I have, in fact, this organic here, which is this van der Waals gap. So which means that I can get away. I don't need a very strong solvent to dissolve this. And in fact, that's what we find. That's why we can get away with a solvent which is slightly lower donor number in order to dissolve the 2D. Okay. And so I can do this with 5 to 18 and get something which is a 2D perovskite, which I can dissolve, which can dissolve in these solvents. And so now I can take these and do spin coating on top of a 3D perovskite. And in fact, that's what we did. Here's the 3D and that's your 2D, right? And in fact, I can do this one by one. So this is your 3D absorption, which is the purple curve. And then you put an N1, which is this black. You could put 2 and 3 and 4. And now you see this follows this memory seed approach. You can get very pure 2D, all, which is basically on top of a 3D. It's like a stacking layer on top of it. And that now shows you that you can get very thick layers of this 2D by using this design principle for these solvents. Okay. And now what I can do is I know these band gaps of the 2D and I know their energy levels. I can now pick, I can use them as selective contacts. For example, it turns out that for a 3D perovskite here of a band gap of 1.6, you can see that if I want to inject an electron right into a 2D, it's too high, which means there's a barrier for the electrons, but there is no barrier for a hole if I pick this layer here, right? The holes can go through seamlessly. And in fact, that's what we find, that I can make these devices which are called NIP. Essentially, you have holes which will go from the perovskite to the this N3 layer of the 2D and then go out, and I can control this charge transport through this behavior. Whereas if I make a PIN device where I try to move an electron, I get some passivation effect in the beginning, which is what I showed you earlier, but then I get this precipitous drop in my power conversion efficiency. Okay. So this is good. And then of course you can scale this method up. Now we have made some modules which are about 50 centimeters square, and this is a scalable method, which is kind of in review. Okay. Now, when we looked at the stability of these type of devices, you see that this is a stack of the 3D and 2D, and you can see that now it gives you stability, which is over 2000 hours without any degradation. And in fact, this was done at 60 degrees C, not quite at 85. But nevertheless, this was really a record at that time. And you can see now this is the 2D perovskite by itself. And now I've added the 3D on top. I'm sorry, the 2D, I've combined them in this way, and then I get this really nice stability. Whereas if I put very thin layers or use previously used strategies, then I don't get very good stability. Okay. Great. So, Saikiran, how much time do I have?
You still have 10 minutes, 10,
10
15
minutes.
minutes.
Okay.
Yeah, 10, 15 minutes.
Okay, great. So this was very good, right? I showed you a method of combining these two things. But the question that we wanted to, as I said earlier, is that what we wanted to get was to get stability at 85 degrees C. And so I showed you the stability, which was at 60 degrees C. But as soon as we went higher, we found that, in fact, the stability wasn't very good. And so we came up with a new approach of doing this. And so let me take you back to these perovskites, right? I showed you that this is the 3D perovskite, and there is this conundrum where only MAPI is the one which is kind of stable, but it's really bad in terms of environment because the moisture stability is terrible. So what you really want is this type of a FAPI or a cesium lead iodide to be stable. And the reason for that is because first, that if I look at the band gap of formamidinium lead triiodide, it's 1.45, and it presents itself very favorably to the maximum power conversion efficiency that you can get from a single junction cell, right? So you can get something like 34% at 1.4, and this you can get very high conversion efficiencies over 32% or something like that. Okay. But as I also mentioned that there is this issue where at room temperature it exists in this yellow phase, right? Which is these type of, this type of a layered type structure. And these are not corner sharing, but these are sort of edge sharing or phase sharing octahedra. And so it only turns to its black phase, which is the photoactive phase or the perovskite phase, when you heat this to 150 degrees C, and it undergoes a phase transition and you can get this black phase. Okay. And in fact, you can talk about this in terms of this tolerance factor. You see that this FAPI, this is right up here, right on the edge, and cesium lead iodide is right on the bottom edge. And so you want to somehow, you have to think about a way in which you can compress this lattice, right? You apply strain on this lattice, so you push this down a little bit so that it falls into this green zone, and you can get a stable perovskite. Okay. And so that was sort of the idea that if you could do that, then you could stabilize this phase. And this is nice because FAPI is really temperature stable. And so we thought that this could make a really nice perovskite. And so we developed this design principle. So what I'm showing you here is the lattice parameter, essentially the interplanar distance of the 0, 1, 1 plane, right? This is my FAPI. This is the bulk 3D FAPI. And on the bottom x-axis is the lattice parameter of the 2D perovskites, right? So this is N1, right? You can see that these lattice parameters are very far from this 3D. But if I go to an N2, right, if I make a 2D perovskite where I have Fa as a cage cation, right, not methyl ammonium, but Fa, then I can make a 2D perovskite which has the same lattice constant or very close to that of my 3D perovskite. Okay. So I've shown this here. This is the 0, 1, 1 plane. And you can see this alpha FAPI. This is what you want to do. This is 6.36. And this, if you take this 2D perovskite, now butyl ammonium, Fa, then this 0, 1, 1 is very close. These two lattice constants are very close, which means that possibly I can use this to grow my 3D perovskite on top because these are lattice matched. Okay. So that was sort of the idea, and this was kind of developed by us here and with Jackie Even, collaboration with Jackie Even, who is at the University of Rennes in France. And so the first experiments were very simple. What we did was we took these 2D perovskites on a glass slide, right? And we washed away one half of this glass slide, right? We just wiped it off with a tissue and a solvent, and then we dropped this precursor of the FAPI solution. So this red is the 2D perovskite, and we dropped this precursor and let this precursor flow onto your 2D perovskite, right? And we did this at 100 degrees C. So these are actual, films, and you can see that wherever it touches this 2D perovskite, it turns black. Wherever it, of course, doesn't flow, it remains the 2D, and then this part remains yellow, right? Which is basically, you see, it's about 100 degrees C. That's below the phase transition temperature of your FAPI. If I take this to 150, now this turns black too. But then if I come back to room temperature, if I cool things down, then this part which was not touching your 2D perovskite turns back to yellow, but the middle part always remains black, which is this region 2. And in fact, when you do photoluminescence, you find that this now matches very well with the photoluminescence of your bulk FAPI phase. All right. And so we found a way to stabilize this thing. And in fact, the X-ray diffraction patterns show that this is really an alpha FAPI phase. And we can now do it at lower temperatures, 100 degrees C, as compared to 150 degrees C, which was the original temperature. And it's also stable. It doesn't come back to its yellow phase. And so this is a video, and I can show you this video. let me see if this video plays here. Maybe not. I need to come out of pointer mode. Okay. Never mind. I think this video is not playing, but I think you get the point. And so now, in order to do this in a film, real film of making the scalable process, what we did was we used this 2D perovskite, very small amount, 0.5 to 1 mole percent, and added this into the FAPI precursor and performed these in situ measurements. These are basically you spin coat and you're looking at X-ray diffraction signatures. And we found, we did this for controls and for this. And in fact, what we found was that indeed, you get this very nice conversion, and I won't go into details of this just to save some time for questions. But you can see when you add this butyl ammonium, you get this very nice 3D phases of the FAPI, which is now, and in fact, the lattice constant of this 3D film matches very well. In fact, it's compressed now, right? And it matches very well to that of your FAPI. So it's actually a compressed film, which is now contributing, it is pushing your tolerance factor down, right? And it's giving you a very stable FAPI phase. And I'll skip this, but in fact, the mechanism is what I said, is that you have this butyl ammonium, the 2D perovskite, and so this FAPI finds a surface where it can nucleate and starts to grow on that surface of the FAPI, and eventually you get this type of 3D perovskite, which is now nucleated on this templates or the seeds of the 2D perovskites that we have added in here. And in fact, you can get these beautiful optical properties. The band gap is 1.48. This is the lowest reported for a perovskite, for a lead-based perovskite. And you get very nice long lifetimes of microseconds. And these are very, very stable films. Okay. And you get nice devices, and chips. These are about half a centimeter square, 24% efficiencies, a lot of very nice statistics. But most importantly, you get this stability, right? So this was externally validated. This is a cell which was run at 85 degrees C at maximum power point tracking. And you can see that this device is extremely stable now, right? And you get very little degradation. And so this was really the first report of getting this type of technologically relevant or commercially relevant stability in these halide perovskites by using 2D as your templates. And in fact, this also made it to the cover of Science. And so that's the picture here. In fact, this is the 2D seed, and you are able to grow these beautiful, perovskites like that. So, all right. So I think that what I will do is I have lots of things, other things, but I will stop here. But I just take a moment to acknowledge, the group and all the collaborators over the years and the funding for this, for this work. And I'll be very happy to, take answer questions, and if they follow up, you can please follow up with me.